Right. Seem to have solved all the technical issues, switching from Mac to PC remarkably. So it's a pleasure for me to introduce Steve Kevan. Steve is a professor of physics at the University of Oregon, and he has a very long relationship with the ALS. He was actually the first user executive committee chairman, and there's a picture which I wanted to show, but well, switch computer, that shows Steve at the groundbreaking ceremony in 2004, I think. Is that right? No, 1994. Sorry. Yes. I don't know. That has a nightmare. You're really right. Anyways,
the ground was well broken by 2004. I guarantee.
That's true. No, 9, much earlier. Sorry, my mistake. So Steve was always interested in angle resolve photo emission, and most recently has also worked on coherent imaging. But most importantly, he has joined the ALS in July, I think, of this year as the Deputy Director of Science, and we're looking forward to his talk.
Thank you, Hendrik. So I was asked to give a science talk, but I learned something this morning, how to turn that off. It's actually great to be part of the ALS. I've had a really good time for 3 months, and I expect to have a good time for many, many years. This is a great job. It was assembled by Neville Smith, who was my mentor at Bell Labs. And he collected the duties that included going to seminars, talking to smart people. And that's about it. I don't have a budget. I don't directly supervise anybody. So I have a really good job. He wasn't at the talk this morning. Anyway, it's great to be here. I'm having a very, very good time. I'm getting to know a lot of you. I knew a lot of you before. I will get to know even more of you. Most of the last slide before we had the computer problem was involved with communication issues, or a lot of it was. And that, I see that as one of my duties, since I haven't got anything else to do, is to talk to a lot of people. And I hope to talk to you when you have great results and when you have problems and everything in between. Okay, so back to the science. Hidden symmetries in magnetic domains. I'm going to try to convince you that this is a useful thing to do, that systems that don't have very much order in them, you can find little bits of order here and there, and those little bits of order are rather interesting. Another interesting thing about this is that you can use old words and old slides, and they used to be nanoscale, and now you just plug in a new word, and it's almost good for 10 more years. I think the reason this is interesting is I think these are related to intermittency. I'm going to show you a little bit of evidence for that today. Unfortunately, I think the PC won't play the movie, so you won't see it. You won't see the Barkhausen noise. And then I want to end by talking about cosmic, which is the other reason I'm here, I guess. So these aren't our data. This is from data, some results from David Waits' group from Harvard, where they did particle tracking in a colloidal glass, and you can't see this particularly well, but these little dots are colloids, which they pick out in a confocal microscope, I believe. And the big dots are the ones that are fast particles, and that's a trajectory, part of a trajectory for a single particle. It will rattle around for a while as it diffuses in this colloidal glass, and then it will jump. It will become a fast particle and jump for a ways and then rattle around a bit longer. So that's what I would call intermittent diffusive behavior. It diffuses around and intermittently jumps around over a longer distance. Intermittency, I will try to convince you, is an important thing in nanoscale things, but it's only really important if it makes Wikipedia. This is something called a Levy flight. When you can get this image out of Wikipedia, it is a purely mathematical construct. It is diffusion, but it's mathematical diffusion. They put in some longer time tails into the step distribution in a random walk, and it comes out looking something like this. This is a real system. This is a computer simulation. You could probably make this look a lot more like this. This is fractal. It has a fractal dimension of something. I forgot what it is. Fractals are interesting because they're multiple scales. They're all scales, actually. They're power laws come into play, and there is no single scale anymore. Multi-scale behavior is part of the mesoscale process, I think. Several years later, this is a different group, different experiment, but this is X-ray photon correlation spectroscopy. This is dynamic light scattering with X-rays. I believe this was at Argonne at APS. similar system, a colloidal glass, and this is a function which basically measures how rapidly a system decorrelates with itself. And the point they make in this is if you get too close to the glass transition, I believe it's this one right here, is the dynamics. You can think of this as simple kinetic behavior. The kinetics become anomalous. They become, in this case, a stretched exponential. And you can go between those two in this system by changing the temperature by just a few tenths of a degree Celsius. So this colloidal glass, which might look something like this, again, it's a different experiment, but it's very similar in execution, has strange kinetics and intermittency all in the same thing. And I think those are related to each other. How do these intermittent events, what causes them to happen? Why does a particle decide it wants to take off and diffuse over a longer distance at a higher speed? A couple years after that, again, not our experiment, one that's gotten a lot of discussion but not much follow-up. This is a paper by Wachner and company from Hamburg mostly on, again, a colloidal glass. And they do, they're looking for hidden symmetries in this thing. They take a coherent X-ray beam, so they take an X-ray beam and spatially filter it, scatter off of this colloidal glass, and it makes a diffraction pattern in the far field, and it has this ring-like structure because there's no obvious azimuthal ordering in this thing. And they calculate a correlation function, angular correlation function, which basically compares this ring to itself, a rotated version of itself. They do that continuously as a function of angle. And this is what you see. This is the pattern again. This is the radial distribution function. If you look carefully, you see these oscillations. So there's a 4-fold, 1, 5-fold, 4, 10-fold. They see all sorts of symmetries around this ring in this correlation function. Again, this is a regular normalized correlation function. It's regular. Compare the intensity at some angle with an angle plus some increment, and then you plot that as a function of the increment. And so these symmetries were very interesting. They interpret them very simply, I think very plausibly in terms of local structures. In this case, it's a 5-fold, maybe an icosahedral structure or something like that. So they're picking out bits and pieces of symmetry, local symmetry in this otherwise disordered glass. It's a plausible explanation. I'm not sure I believe that actually, but it's a nice idea. So the question is, are these symmetries matter? I think they're interesting, but do they matter? In this case, they would matter to me if these symmetries are somehow connected to the anomalous diffusion and the intermittent behavior. So somehow, say this is very stable, so maybe this doesn't diffuse, this doesn't make fast particles, but maybe other areas have other symmetries that would make a fast particle, for example. And that connection between what makes intermittent events and the local symmetry, actually, you can find examples of that all over the place. Another one is here. This is an old image from Jeff Courtwright, actually. It's a domain labyrinth, a magnetic domain labyrinth in cobalt platinum multilayer. This is a perpendicular anisotropy film, so these domains are either in or out of the plane. And the question I have is this film at thermodynamic equilibrium? And you have to ask, can you write a precision function, basically? And you can't really, because on the scale of many domains, this is not at equilibrium. I guess the easiest way to see that is the magnetization is not single-valued. You've seen magnetization loops, and at a given temperature and applied field, you can have a whole range of magnetizations. Magnetization is a good thermodynamic quantity, but it's not single-valued, so it can't be a thermodynamic equilibrium. It's also essentially static on any reasonable time scale. These domains are essentially entangled in such a way they don't move very much at all. There's many metastable configurations in this system. When you switch a magnetic system, it's a noisy process with lots of intermittency, and I'll be talking about that more or less for the rest of the talk. On a short scale, it is at equilibrium. Inside a domain, the magnetization is pretty well defined by the magnetization curve. We know what the fluctuations are and so on. So I think mesoscale science, it is in part a crossover between equilibrium at short-length scale and non-equilibrium at long-length scale. And that thought belongs to both this magnetic situation and to the colloidal glass. There's many other instances where you can wrap mesoscale science, whatever you think that is, into those words. We all have our own idea what mesoscale science is, but those are mine. You may have seen this demonstration. This is actually from one of Feynman's textbooks. You can see on YouTube as well. A magnetization loop is not a smooth curve. It's got these little jigs and jags on it. These are Barkhausen cascades, where the magnetization will get hung up as you change the field, and it will stop changing. And then all of a sudden, the magnetization will change quickly. And that is a Barkhausen cascade. So again, this is a system which is close to equilibrium. It's got this sort of mix of equilibrium and non-equilibrium components, and it shows intermittency, and that intermittency is something like the colloidal glass, the diffusion in the colloidal glass. Comes and goes. You can actually listen to this stuff if you pick it up on a coil and amplify it. You may have seen that demonstration. You can see this in a Kerr microscope. This is a paper several years ago, basically looking at, I believe this was just a cobalt film, but looking at the domains in a cobalt film and measuring the spatial range and the magnetization jumps of these Barkhausen cascades. And there they are. This is a sort of a magnified image of a real loop as opposed to a fake loop that I put together. They actually show self-similarity. This is, I think these are the probability of having a certain jump and according to avalanche size or something like that. And they plot on a log scale, plot as a straight line. These things roll off at large length scale because this is a microscope and the cascades get larger than your field of view. But this has some self-similarity, and it's got a power law behavior just like the fractal behavior of a Levy flight. Just like. Okay, this actually matters. This is a cartoon that Sujoy Roy put together, and it sort of says it all. Something we want to do, we want to make sensors. In this case, it's a colossal magnetic resistance read head on a magnetic hard drive, say, and you had these bits flying past, and this is this complex oxide, which some weird ordered phase of orbitals and spins and whatnot. And you try to use that to read the magnetization because these things have a large magnetic resistance. The problem is if you make thermodynamic measurements of these materials, this is resistivity versus temperature, and it sort of does this, but that's not the interesting one. This is resistivity versus time, and this thing is jumping up and down. There's intermittent behavior in the resistivity of this complex oxide. This is a material with lots of sort of self-assembling mesostructure, I guess I should call it now, not nanostructure, but in any case, these complex oxides are intrinsically, they seem to be intrinsically heterogeneous, and the heterogeneity rears its ugly head in this sort of thing. So this matters in real devices that you'd want to make. When you make things which are small, intermittency tends to be an important thing. It's important. How do we measure it? How do we control it? And I'm here to tell you how. We want to do coherent X-ray scattering. This is the same technique that the colloidal diffusion current was done with. You take an X-ray beam, spatially filter, scatter off of a complex material, an oxide, say, and you get a diffraction pattern, a speckle diffraction pattern in the far field. And that kind of maps this complexity in a diffraction pattern where you can use it to look in the time domain, to look at slow dynamics. You can use it in the space domain. You can do diffractive imaging. We can do various metrology techniques, and I would say these symmetries are an example of metrologies. So just a few observations. Many nearly degenerate ground states lead to intermittent dynamics. Anytime you have a system with many degenerate ground states on some length scale, if you try to make that system change, it will have intermittency. Things crack in intermittent fashion, for example. These often lead to power laws and fractal behaviors, from earthquakes to sand piles, I guess. Macroscopic rate laws are often anomalous. Stretched exponentials are an example. And just Google nanoscale intermittency if you don't believe me. I did it one afternoon. In half an hour, you have dozens of examples of this. Probably the best known, most actually studied now is these blinking of quantum dots and other fluorophores. Questions. Are there organizing principles? This is such a cool paper back in 2000, and if you haven't read it, I recommend that you do, because it's come back into vogue in the age of mesoscience, where they talk about other organizing principles of this sort of thing. What's the connection between local order, like these symmetries that we're seeing in the colloidal glass, and intermittent events? That's probably the key thing. These symmetries are interesting, but they're only interesting if they're related to something important. And how do we control them? These are sources of noise. How do we control them? That's even a harder problem. So let's go back to this. This is this domain labyrinth again. It's got frustration and unequilibrium. The loop in this case can be kind of skinny, low remnants and low coercive field, and that's important, we think. We illuminate this with a coherent soft X-ray beam in resonance with a cobalt L-edge, where we get large magnetic contrast to make a diffraction pattern in the far field, which looks suspiciously like the one from a colloidal glass because there's a characteristic length scale, and you get a characteristic scattering angle or scattering wave vector given essentially by Bragg's law. So are there hidden rotational symmetries in these labyrinthine phases, and the answer is yes. They're actually kind of easy to see, and I'm embarrassed we didn't see this 10 years ago because we've been taking these things for a long time. This is this pattern like this expanded out. We do the same correlation function that I showed a moment ago. You compare this pattern to itself, a rotated version of itself, and average that over the whole pattern. We do it a little differently, actually. We actually unwrap this into polar coordinates. So this is now Q, this is angle, but we can convert that to scattered wave vector, and this is angle. Sometimes use delta, and sometimes use, yeah, there's delta, it's delta. And you can see already, that doesn't show up particularly well here, but there's this sort of beating structure here, a bright, dark, bright, dark, bright, dark. And if you look carefully, that's an 8-fold periodicity. And if you sort of do a line out of that line of pixels, you get a nice 8-fold pattern here with some spikes, which are due to the speckle. We understand these two spikes in good detail. If you do a different one out here, then there's not much to see. That's actually a real signal, and there are higher frequencies there. There's sort of an absence of low frequency, I would say. So they're certainly there. So are they related to Barkhausen events? We'll come to that. You see a lot of different symmetries. That was an 8-fold one. We commonly see 6, 8. We see a whole bunch of them. They're all even periodicities. We've seen up to 28-fold. There are no crystal symmetries of 28-fold symmetry axis. They're mostly factors of 2 pi, but not always. We have 14-fold here, and that doesn't divide evenly into 2 pi. Rapid evolution with wave vector, I didn't show it before, but these things are actually pretty localized in Q. They evolve slowly with H, and this is what we'll get back to in a moment. These are fairly rare, and characterizing these things, by rare I mean you look at a pattern, there might be 10 or 20% of them have some dominant symmetry, but there's a whole bunch of candidate symmetries because they come at all different wave vectors, so they're pretty rare. I can't give a good estimate of that yet, but they're not very common. You have to look kind of hard for them to find a lot of them. Fortunately, we can take these patterns really quickly. We see a lot of them, a lot of up to high order. And is this a new way to classify disordered materials? Is it just due to finite sampling? Is it both? It's certainly due to finite sampling. We've more or less proven that. I won't go into the details. But we have a field of view limited by our spatial filter pinhole, which is microns. And we're sampling, I don't know, several thousand domains or something like that. So this is definitely a finite size effect. And you might just dismiss it at that point, say it's not interesting. Most of nanoscience is a finite size effect, so I reject that argument. If I can relate this to something interesting, I say it's still useful to do. It certainly is a way to classify disorder, but it's not clear what that classification means yet. But the question I want to ask is are they related to Barkhausen events? So to do that, you want to measure these as a function of field. And what I'm going to do is take a whole bunch of scans like this. Actually, I should go back one more. Scans like this, unwrapped scans like this, and basically do a cosine Fourier transform along this axis to get the spectrum of these periodicities and plot that versus field at various wave vectors. It's a multidimensional data set. So here's different wave vectors, different scattering angles in that annular region, inside the donut, outside the scattering distribution, as a function of magnetic field. And you see these things evolve as a function of field nicely, I guess. There's actually not much happening here. They generally last for a long time. This takes you through most of this field excursion, one branch of this loop. I think we're on the blue loop here, if I'm not mistaken. So there's actually not much evolution here. There's a little bit. Occasionally they come and go, but they're pretty much constant. Once you have one, you can change the field, and it doesn't change very much. What that's telling you is that when you change the field in this system, and if the system is really well defined like this, when you change the field, change the magnetization, what you're really doing is just moving these domain walls a little bit, and the white domains become black domains, and the black domains become white domains. So you sort of change the magnetization by breathing the domains a little bit. So there's no big changes in topology when you change the field, at least in this sort of region near the remnant field and remnant magnetization and coercive field. Okay. Okay, so that's all that says. You can actually change that. This is a really old figure from some original data from this kind of measurement. This is a cobalt platinum multilayer. This is a really smooth film with nice domains, and as you add more and more disorder by how you grow the film, you get less and less well-defined domains, rougher and rougher surface. And it would be lovely to be able to do this Barkhausen experiment with variable disorder like that. Unfortunately, these samples went to sample heaven a long time ago, and we can't do that. What we do have is another sample which Eric Fullerton made for us a couple of years ago. This has a larger remnant field and coercivity. More importantly, the domain period, as you change the magnetization, changes by something like a factor of 2. So that domain doesn't just breathe. The periodicity is changing a lot. I don't know of any way to do that without having some changes in topology. So if you look at the same plots, this again is applied field going along from here up to there about. And this is, again, the symmetry components from 2-fold up to 30-fold in this case. There's a lot of action here. It looks intermittent to me. And this looks like Barkhausen noise. Of course, we're not listening to it, but we're sort of seeing it. This is supposed to be a movie, but the movie is dead because I'm not on my Mac anymore, and it wasn't a very good movie because it didn't convert very well. Anyway, this is a movie, and it really blinks off. All these things blink off and on, really in a seemingly correlated random way. So it would be nice to say, gosh, this really is a Barkhausen event. When this guy just goes away, it's a Barkhausen event, and we have some relationship between local symmetry and Barkhausen event. We're not there yet because we don't know how to measure what a Barkhausen event is in this experiment yet, but we're working on that. So it's sort of an indication that maybe there's something there. What are these things in real space? Let me just take 30 seconds to try to show this. This is an MFM image of a random domain pattern from Eric's group, Eric Fullerton's group. If you take that and do an autocorrelation function, that's called a Patterson map or a pair distribution function. This doesn't look very promising. You don't see any symmetry here, but you started to see something, maybe there's some symmetry in this one. Transform that to polar coordinates, and you get really a dazzling looking thing with faces and all kinds of stuff, and this is really fun to look at for a long time. But interestingly, the lower periodicities are down here. You can see a nice 4-fold symmetry along right here if you look carefully. There's a 12-fold symmetry right here, sort of cutting through the foreheads of the faces, I guess. What we notice is that where these symmetries onset, this 4-fold symmetry onsets at this pixel value and so on down to 16-fold, you basically take the circumference of that radius, of the circle of that radius, divide by the period of the real space period of the domain, and it always ends up about 1. So these symmetries, in real space at least, correspond to when you can pack a bunch of domains in a circle. That's sort of a geometric criterion for in real space where these symmetries come from. And somehow these symmetries you see down here transform into Q space to give the symmetries we see in the speckle pattern, we think. You do see that you can do that, so they do. Okay, so I'm done. I think intermittency connects dynamics and complex kinetics, and it's nice because dynamics are very interesting now. There's lots of interest around the ALS in doing dynamics. Complex kinetics is always interesting. We need to measure and control the intermittency in real devices. I haven't mentioned this much, but I've gone back and forth between real space and Fourier space a couple times here, and I think that's very, very important. These systems, you really want to be able to measure things statistically and with scattering, and you want to go in and look to see what you're scattering off of too, to see what the symmetry is or something like that. See a lot of power laws, and that really means you need broad spatial and temporal sensitivity, and that means you need a lot of signal, and for that we're building Cosmic, and maybe I'll just stop there with a picture of Cosmic. There are 2 workshops on Cosmic in the next 2 days, and I encourage you to stop by if you're interested. And thank you.
Thank you, Steve. While we are setting up for the poster slam, are there any questions for Steve? Jeff, please.
So, Steve, in real space imaging, there's Zerbicky polynomials, which are an orthonormal set of functions that can be used to build up an image. I would guess that in reciprocal space, there is also an orthonormal set of functions that can be used to build up an image, and that might be related to what you see.
Gosh, Jeff, I'd like to talk to you about that sometime. I have no idea what you're talking about. It's an interesting point. We're looking for interesting topological explanations for this, and we're still scratching around for the right way to think about it.
Any other questions? Well, Steve is around at the ALS.
I'm here also.
He already tied his research into the Mesoscale initiative very successfully, I think. It's very quick thinking on your feet. So let's thank Steve again. And